All right, so we're going to do procedural terrain still, but we're going to step away from the terrain for a little bit. We're not just going to be looking at code. I want to be looking at force graph. So force graph is this generation of having a whole bunch of items that are connected together, and we want them to establish a balance of how they unwind and get developed inside of a level. This can have a lot of meaning. We can have this in 3D space. I'm doing this in 2D space right now. But effectively what you're watching is these things unravel into shapes and patterns that are a little bit more unwound. They're natural in appearance. So if I run this again, we'll get another random set of shapes, and then it tries to unwind them. So it takes a few iterations, but then it finishes. And that's not bad. There was some crossover, but it's not terrible. This one did a good job of unwinding itself within the limited iterations. Now, if you're already comfortable with this stuff, I'm planning to put a number down in the description to say where you can start seeing the code for this. And I'll explain the steps of it. And this is both a force graph and a force graph visualizer. So you kind of have to have both to make sense out of the force graph itself. But the force graph math, we're not doing anything beyond like linear algebra, barely even linear. Well, I guess linear, I don't know. I'm not a mathematician. I'm just teaching you procedural geometry. So I will occasionally have some words and phrases wrong because a lot of this is self-taught. Okay, so let's dive into this a little bit further. I want to first explain some of the iterations and processes you get here. Now, even for those who are well aware of how a force graph works, there are things in the nature of it that, depending on the numbers you put in, will wildly change the nature of the results you get out of it. That by changing the movement force, how much force we're applying to each node to allow it for freedom of movement per step, that can completely change the outcome of whether or not larger items are on the outside mostly or on the in. And I'll show that briefly. There's other things that influence this, but you can use this to create rivers. You can use this to create groupings of things. You can have separate things, some nodes being processed in 3D, others being processed in 2D and still affecting each other. You can have items that are being balanced so that they don't get pushed around by other things, but then other things can be drawn to it. You can create lots of interesting structures here. Okay, so let's do a little bit of explanation. So the first thing is when I click this is a hack. It just basically turns a Boolean checkbox into a button. So I'm generating this. It's generating 25 items. And now there is a 7% chance that they will end up connecting. Now, here's what that means for that percentage chance, by the way. Not that it matters too much, but that is 7% of 25. So all the nodes are likely going to be connected under 7%. Because what is that? That's like 3. That's about 3 per. That comes out to about 3. So that means a lot of these will have up to 3 or 2. What is it? Oh, no, I'm dividing it by 7. So it has a quarter chance. So each one of these has about 25% chance that it will actually cross over to another one. Let's increase that to, let's say, 50. Let's go to 100. If I make it 100, this is what it looks like. Everything is connected. Everything is pulling itself and pushing. So because the items are pushing away from each other as well, that means that some of these literally cannot get far enough away, but they also are getting this stronger and stronger pull towards each other the farther away that they get. Now it also has an iteration stop. So this one we say after 200 times it stops because this has to be a balance. It'd be nice if I could just let this process forever. Which if you're doing like a nature simulation or something like that, and here's how some of the plants are flowing and growing out, this might work great to just leave on all the time, and it's constantly influencing and changing how things are working. You could even skip the idea of using this on a map and have a bird shape on here or an octopus shape on here, and you draw points of attention to its tentacles, and then this will kind of pull its tentacles off towards that direction, and then the whole thing will start to go with it. You can use this for all sorts of things. but I want to call out how we're going to use it for terrain right now. And hopefully you can extract out some of the other ways that we can use this for other ideas and interesting concepts. I'm probably going to go make the squid concept at some point. All right, so iterations to stop. That's effectively how many frames we're going to allow it to continue processing, because most of the time we want this to execute and then finish so that we can use it to procedurally generate something. In that case, we don't even need to keep a pool of information. We don't need to keep it there. It's only there temporarily to gather some metrics. So we have a visualizer on it so we can see it. Okay, move force is how much it's going to move. If I increase that number to like 10, look at that. This is chaotic. This is fighting itself really bad. If I reduce it, let's allow this to go infinite for a second. I run that. Let's put this down to 0.1. Look at that. That is so much slower. The things are not forcing everything way out of the way. Things are kind of all staying in one spot. So it's because of that chaos, the amount of force it can apply, it is allowed to break a boundary of where it might end up. In this case, we don't want it to be that much. So let's see, like 1. We'll still see some movement with 1. There's some flow in here. It still drifts a little bit, but its drift is nowhere near what it was when it was up to 10. Now you can see there's this red dot exposed. That red dot emphasizes the anchor, because if I didn't have this anchored to a point, 1 frame might allow this to go 10 meters off to the side, and in 3 frames we won't be able to see it anymore. Because this is an engine. It can make itself move. So I'm going to put it back to 1 so we get a nice flow. It kind of finds its way back over to here because that's how the flow works. Okay, but I don't want it to run for that many iterations. It also shouldn't normally have this many things. I could put this really low, and we could also go to a high number like 100, but that again is not something that we're likely going to want. If you were to look at a map for StarCraft, and you were to see this many key areas in it, that's chaotic. You don't really know what to do and think about that one. So this is a lot harder to get something useful out of. So we want to still get some value out of this. And so we need to think about how do we organize our terrain and our design. So a lot of the design is going to be influenced by that. And we want to break this down into smaller components. Like the first thing is, what are the major points of my island? Well, I'm going to need multiple bases on there. And they need to be a certain way away from each other. I don't have distancing in this one. Everything is still pulling at the same rate as each other, but that's something we can apply. But I need to have some items in there. So let's see, I might only have like 8 items being pulled out to begin with. Now I'm going to want more connections in that case, a higher chance of connections. So it generates these, and the lines would effectively represent, we could use them to represent paths, that we guarantee a path. Now, just because the line is straight here doesn't mean it needs to be represented in a straight line in what we are creating for the end island. Just like the Perlin noise can create all sorts of fluctuations, we can use similar tools and operations to generate all sorts of terrain shapes and path shapes. Okay, but these might be bases, there might be open areas to battle, there might be key areas where we have things converge that, or confine. I can't remember the keyword, but when you have tight walls on areas so that everything has to come through one narrow point. But anyway, there's lots of things that you can design into this. Now, I don't want that. I want a higher number than that. So probably around 25 is more reasonable for what I find myself using with a lower number of connections. And key thing, the connections will be purposeful. They'll be generated. So let's dive into the code and take a look at this. Okay, design part stepping aside. I will be explaining a few points where we can influence it in here and where we affect things in the math. But in general, here's how it goes. Okay, so to begin with, we have all these public variables that we saw before, and I stepped through what they were doing. But then we also have a private list of all the nodes that there are. So if we generated 100 nodes, here they are. We use it primarily just to destroy them. Okay, well, and to apply their forces. So yeah, we need them a lot. And then we have iterations remaining. Iterations remaining are basically the countdown of saying iterations to when we stop. Well, we set it to 100 and we just subtract and keep going. Okay, so the first thing we have in here is instantiating. We want to create the items so we have some items to work with. There is a little bit that goes into that, so let's take a quick look. Yeah, it's right here. So first, we set the iterations remaining. So we just reset it when we click the button that instantiates the random nodes. And then we destroy all the existing ones and clear out our references to them. So we just wiped out the old stuff. And honestly, don't worry about using a pool for this. The efficiency is not necessary in most cases. In most cases, this is used to procedurally develop something that then the fact that there were processes involved in the generation of it do not have any need to stay in memory. And they can just disappear. So like the creation of an island or level, this is usually one thing that happens at the beginning. Okay, so next thing in here, we're going through every single item that we're requesting. We're requested a certain number of them to be created. So we create all of them, giving them a number in the name to separate them out. And then there's two ways that we can set a position, a starting position. Inside random unit circle or random unit sphere. Circle keeps it in 2 dimensions. And for most cases, most games, even if they are 3D, are still effectively developed in 2D. StarCraft 2 is a 3D video game. Most racing games are 3D racing games. But also StarCraft 2 and most racing games are still managed in just 2D space. It's a surface that things are on and moving across. And yes, some things will be higher and lower, but that doesn't affect the physics as much as in general. It doesn't affect the structure of the world. It is that flat surface you're moving across, whether it's a racing game or StarCraft. Okay, but if you do want to go into 3D, which you can, and have this generate things like crystal structures or whatever you want, this can do it. And use 3D. But if one of the axes has a 0 in it for all of the variables, none of them will ever push that variable in any other direction. It'll stay at 0. Okay, so then we also add node. Node is what effectively allows the connections and remembers them. Okay, now we need to assign the connections. First thing is I'm putting a cap on this. So once it is possible to exceed the cap with the way this code works, but in general it does not and helps keep the numbers in the correct ranges that we're looking for. Now again, this is just a random distributor, so you're creating whatever random nodes you want or whatever nodes you want to define it. So you will have, I want 4 bases, I want 2 mountains, I want 6 resources, I want whatever, and you just drop them in and then this produces it. Okay, but this one, I'm putting a distribution cap, which is basically saying that we take our percentage of like 10%, and then we put it by we multiply it by our instantiation count of say 100. So if that's the case, then it's 10% or 0.1 times 100. So we get 10 out of it. Our distribution cap is 10. Next, we go through every single node, and when we start out that node, we're going to say, if our connections are greater than our distribution cap, if we already have 11 or more on this particular object, skip this. Skip this. Now, this primarily affects the ones that we get to later because there's more chances for things to be connected to the objects at the end. Sort of. Anyway, next we go through a secondary loop where we say for j equals I, we start at where we left off with the I plus 1. So it's not going to take that first object that was already there. We won't have a cross-reference where it references itself. Okay, so then it goes through the rest of the objects. You'll also notice that on the I, when I'm iterating through these, it's the I is less than the instantiation count minus 1. So if we have 100 items in there, this will say it's as long as it's less than 99 because we're going from 0 to 99. And then this is going to effectively go to 99 or to 100. So it's less than 100. That way this one peaks off at 98 and we will still have one comparison to the end. All right, So technically the last one, nothing ever sets it. Only, or nothing, it cannot set anything on itself. Only other items can have made that connection to it. Okay. Oh, and the first one, nothing else can make a connection to the first one. The first one can only make connections to others. Okay, so let's take a look at this. The second thing is we're gathering node J is the reference to the J index, and node I is the reference to the I index. And we're going to say, is there already a connection? Are they already connected? Okay, continue. If not, then we're going to check to see if, based on a random number between 0 and 1, if that number is less than our percent chance. So if we have a 0.2 for our percent chance and this came out with an 8, whatever, it isn't going to work. If it's a 0.1, it will work. And it will create the connection both ways and then move on to the next iteration until it's iterated through everything. Okay, so there's our connections. Next, we need to visualize this stuff. We have to be able to see what's happening. We handle that in onDraw gizmos. So onDraw gizmos, first thing we're doing is we are setting a color. If you haven't used this before, you do have to have gizmos on. If I turn gizmos off, you can't see it. But that's also how you see your camera. There are ways that we can set this up so it only shows up if I have the Force Graph Manager selected. But again, this is a visualizer. In your game, you likely will not have this. You'll only be using it for tuning. Okay, then let's go back. Oh yeah, same thing. In the game, you can turn gizmos on or off. Gizmos do not show up during the production game. It only shows up in the game window if it's part of the editor. I think there is a way to turn that on for gizmos or handles or something in there. I don't remember which. But by default, it's not something that you can use or should use inside of the regular game. Oh, let me turn that back on. I want my gizmos on. I want to be able to tell where my camera and my light is. Okay, so gizmos are on. Anyway, so the first thing we do is that center mark at 0, we're just saying draw a sphere at 0 and make it red. So we set the color and then we tell it to draw the sphere. Next, we set the color again, this time to green. And I'm basically going through every single node and every connection on those nodes and telling it to draw a line from node to N2, from the first set of nodes to the second one. Now, in this one, that's only for connected nodes. Our previous code made sure there were no cross connections, but this does actually duplicate the lines. So 2 lines are being drawn. One's being drawn from the one side to there, and the other one's being drawn from this side to here. Big deal. This is a small drawing test tool. It's for debugging. It's not for performance. It isn't something a player will see. The last thing that I draw is the actual nodes themselves. I tried drawing this in the previous order where I had the lines being drawn last, but the lines overwrote the circles identifying the points, and in some cases the points became very hard to notice, even without that many lines in there. Okay, so next, after this, we go to update. Update, all it's doing is I've got my button hack. This is effectively the way that I call to instantiate the nodes. We could have another function doing this. It doesn't need to be done this way. This is a designer tool. Then we're telling it to apply forces. The first thing apply forces does is it actually checks to see if we have any iterations remaining. And if we don't, it just returns right away. That could have been up here. Whatever. Okay, so we're applying the forces. This is the point in the frame where we're deciding how much each element moves. Now, I will call out that in a lot of the other formats I've seen for this, what happens is each one gets a velocity set, and then the object updates its position every single time. That means less math has to happen. You can actually put coroutines on and run like 30% of your nodes, of your crossover nodes, so your performance stays nice. But then the items move. Now, they might start moving towards each other and actually overlap by the time that the coroutine catches up to processing one of those to say, oh, you're getting close. You need to start going that way now. And so now it's starting to go like this. So it can change. You can control a lot of things there. But in mine, I'm literally moving it per frame, because I don't want the velocity in there. I don't want to process the velocity. I want to basically tell each thing to move and get the visualization of this out of here. The visualization of this is going to be in the final shape of my terrain, of my level. Not just the shape of the terrain, but the objects showing up on top of the terrain, the details, the animals, the trees. What's going to be there? I can let this help dictate that. Okay, so going through this, I'm going through every single node, and I am applying a pull to 0. If you want an anchor to make sure, because remember, things can start distributing wherever they want to. And that might be an effect you like, but in general, at least the way I tend to use it, I keep it structured. I tend to keep these things close together, and then I use other factors in here to stretch it out as necessary. Okay. Everything is pulling to 0. Another way that you can do this is you can give everything multiple sets of connections. So half of it is connected to A and half of it is connected to B, and they're at random points. And then another one, and then you also have a center point they're connected to. So everything's trying to get to here, but it doesn't want to cross over sides. So you end up having kind of a split between your levels. And you could even put a couple of them with weaker strengths along the lines, and then you can create a yin-yang shape if you want to for how this pattern is. There's a lot you can do here for how your items are connected. Now, everything in mine, the forces are applied equally, so I don't have any differences to say this connection is stronger than this one or weaker than this one. Nothing is applying that like that. Okay, so we're applying a pull, so everything goes to the center right now. Next, we're going to go through every node again, and we're just going to say, well, okay, if the nodes are the same, then we're not going to apply this. Because here's an important thing. Every node, you remember how it's connected both ways? I'm only applying the pull to the first node. I'm not applying it to the second one, even though they're connected. One might be connected to one while the other one is not connected back. So one could be drawn towards an object wherever it's going and just follow it around the level. While the other thing is influenced by its own set of decisions. That's a great way to do this, because then those things, you're only needing to apply and go through the connections. In fact, another way that we could do this is really all we need to do is go through every single connection on here. And that's kind of what we're doing. We're going through every node and then every connection every node has. That's effectively the result. If I kept a separate list of the connections, then I don't need to do this duplicate check through all the nodes, because a lot of times they're not even going to be connected. Okay. Now there is an importance to going through each of them, because I want them all to try getting close to 0, and then I also want them all to push away from each other. So I still need to check values. Like, even if something isn't connected to anything, I still want to make sure they're pushing apart and we don't have overlap. Okay, but if they are connected, if I check to see that the items are connected, that yes, node 1 contains a connection to node 2, then I'm going to apply a pull between those, so those two start to try to get closer within all this. Now, as those are getting closer, of course, that changes the shape and dynamics of everything inside it, so more of these looser items are going to start getting pushed to the outside. All right, so there we go. That's effectively how it works. Every item gets a push, some items get a pull, and everything is effectively getting a pull towards the center to kind of keep it anchored. Again, lots you can do here. But how does the pull and the push actually work? The functions are almost identical. So I'm going to expand out both so you can see them side by side here. So they both take the same parameters. N1 to position, the position's targeting going towards, and the distance. We could get the distance out of there, but keep in mind that we're potentially passing this in through two separate functions. Why process the distance twice? Why do square root functions? Square roots can be expensive. So I want to reduce those where I can. So my distance, I'm passing it in as a parameter. Okay. So now I'm getting the difference. So I subtract one from the other to get the difference. And that's saying here's its distance apart, here's its direction apart. I can extract both of those. And now I'm going to extract its direction, which is basically the normalized difference. Okay, now I need to figure out how much force to apply here. So for the force, it's basically equal to whatever we said the move force was, which is usually between like 1 to 2. And now we're multiplying that by delta time. There's an issue there I'll get back to. So it moves smoothly from frame to frame, even if the frame rate changes, sort of. And then we apply the direction. So if we didn't have this in here, we could just have a slightly lower, we could have a lower move force, like 30%, 1/3 of what, or 1/30th to 1/60th of what the current move force is, and we could skip the delta time. So that times the direction. So it's normalized direction, and that says, okay, well, we're pointing 1 up and 2 over to the side, so we're basically going out at an angle like this. That wouldn't be the numbers. Because we need a 1, it needs to equal a 1 at the end, but whatever. But we're heading out to a particular direction. Now we've multiplied that by 8. So now we're going this fast to get there. And then finally, we are multiplying this by some value between 0 and 1 that effectively says how powerful the force is in this instance. So in this case, we're using distance. Now, if distance, I'm clamping it, whatever our distance is, to 0 to 1. If I change this 1 to a different value, that effectively can change the strength of how much it pushes things away. So right now, it's limited to 1. It cannot go beyond that. But if depending on what I'm doing, I have to clamp this differently. I have to put a different subtractor here, and these values should effectively be the same. Okay, so my distance in there, I am taking the distance and I'm limiting it to somewhere between 0 and 1. That once we get up to 1, it doesn't matter if it's stronger. I'm not going to push the object any faster. It's not going to go any farther for this. Okay, and then but we need it the opposite direction. We're saying how close are these? What's the distance? So if the distance is 0, they are literally right on the exact same spot. We want them to move away fast. So that means if we're getting a 0 out of distance, we need to do the opposite for our force. We need our force. But if their force is 1 or greater, if it's past that point that we care about, then we don't apply any force on the push. So we don't push. That could also be another thing that I could do here where I effectively do this evaluation first and put an if statement that if this value comes out as 0, then we then we don't even do the next steps. But honestly, in most cases, everything is going to continuously flux in this as things adjust and reshape. Okay, the other one is pretty much exactly the same. The only thing that changed is I don't have a 1 minus surrounding this. And I'm also doing a subtraction of force instead of an addition of force. That's it. That's the only difference. There's the code. So this is a force graph. There's a lot more nuances that we can get into and that we will get into in some of the future stuff. This was a little bit of a larger video because there's so much to it, and I've been trying to hold back on expressing so many amazing things you can do with this. But for now, that's the explanation of a force graph, and we'll get into the details and designs of how we can use it later. For comments, one thing is if you've used this to manipulate and do strange things inside of your terrain or inside of how objects move or animals move, please share that out. I'd love to include references to that and see how other people are using it. I've got my methods, other people have theirs. There might be some wildly differing things, and I'd love to learn some more on this. Same thing is if you have some directions on what you'd like to see, there's a lot of this that I've done and have experience with, so I just need to know what people are interested in. And so if you tell me about that, I'll probably be able to share an answer with it. If I don't know an answer, I'll probably be, if I can speak, I will probably be interested in figuring it out and go generate an example for it just to see how it works and what I can do to make it work. Especially if I think it's valuable, but I tend to like the procedural geometry, the procedural dynamics for designing it. I think in a sense, this whole classification of AI I'm working in, I don't know if it has a name, but I'm going to call it procedural AI. That no, we're not working off of these mathematic databases of information, building up all this stuff to make decisions. We have a simple decision being made by the code directly that was hard-coded into it. Procedural AI. Okay. Yeah, that's it. And any other directions you want towards the code for what we create with the terrain and how we might influence that, let me know in the comments. Thanks.